Looks like we're going. Okay, welcome to another exciting computer networks class. I understand that some of you may have had some difficulties with the project build. I can tell you this, that those who email me with their difficulties get special videos made for them. Or I will come into their computers remotely with TeamViewer, and I will work on them over the phone and on the computer, just like a help desk. So if you want to install TeamViewer and send me an email with a time I can call you, I'll ring you up and we'll work on it together. No one who gets help from me is ever allowed to fail in doing a build, even if they don't use the IDE I like, even if they use Eclipse. So if you are an Eclipse person and you want to stick with Eclipse, that's fine. We'll figure it out. And I don't care if it takes me like a Sunday afternoon or whatever. I'll figure it out. We'll make the video and we'll get it working. So I'm not going to let you fail on that one. And I'm sorry we didn't touch base earlier, but you should try and approach me when you get stuck, because that's why I'm here. If nothing else, the reason you could otherwise just read a book and you wouldn't need me. So people do get stuck, and that's sort of important. It's part of learning. I think if you do something and it works the first time, you didn't learn anything. The learning happens when you do something and it doesn't work as expected, and it breaks, or you get bugs. That's when there's learning. So I feel the same way about hardware. If you guys get a transistor or a diode or whatever and you blow it out, that's learning. Don't be ashamed of that stuff. I do that myself all the time. If you're not breaking stuff, you're not trying. So that's why we're here, trying with stuff. You know what we do in the analog class, and I think I just saw a whole bag full of them. These op amps here, these are the blown out ones. I don't know why they're saving them. Put them in a bag. Right? This is what happens when you run a lab. Everybody blows stuff up. They blow things out. That's learning. That's what you're supposed to do. And sometimes the components are expensive. They'll be, I think it was a $40 femtogen module. I don't think that lasted 20 seconds before somebody decided to hook it up backwards. And I said, oh, man. And then it stopped working for whatever reason. And we were like, okay, let's buy a new one. And I think the next time we did it, it probably blew out after about 40 seconds. I'm like, you guys are blowing out these modules faster than I can buy them. I'm going to stop buying them now. You know, that was the lesson. So it's like they took the trash cans out of the subway stations because they found out nobody will throw away their trash in the subway stations if there's no trash cans. So they got rid of the rats, they got rid of the trash. No more trash cans. This is sort of a draconian measure they're doing. I just read about it. So it's one of those things where you shouldn't feel badly about breaking stuff. It happens all the time. So just to sort of recap, this class is really about digital networks. And digital networks are kind of different from analog networks, but we're perfectly happy to talk about analog networks too. Can anyone think of an analog network? Radio? That sounds pretty good. Yeah, actually, you can have analog broadcasts, and they go to a lot of people. So that's a one-to-many relationship. But it's a network, and in fact, you can take the programming from one station and transmit it to another, and they actually call it a network. And they might be like the NBC network, and they all share programming. And they have broadcasters all over the nation. Suppose you think of another, something older, something before electronics. Can you think of a network? Analog network. Well, that's probably the electronics age, right? Morse code. But there was a code for smoke signals. That was a network. people used light and mirrors, and they reflected the light from one mountaintop to another. That was a network, a communication network. Just people talking to one another and passing a message from one to the other. See you guys later. Thank you. That's a network. So analog networking, that's as old as people communicating. So as soon as people started communicating, they were engaged in analog networking. And when people start to think about the social network, right, that's just really another way to say, here's a digital form of an old style of communication. And so people are quite used to this. They've been networking a very long time. Turns out in the electronic age, when people started to work with networks, they had two kinds of networks. Circuit switched, or I'll say switched and unswitched. That's a good way to put it. Switched and unswitched. Switched and unswitched. What would be an unswitched network? Unswitched network. Any idea? An unswitched network? What would be a switched network then? No idea? Switched network? Well, suppose you think in terms of when you called up the operator in order to get a phone connection, right? So what did you do? You would pick up the carbon microphone on the wooden boxed handset, and then you would turn the crank, the 90-volt generator, which would generate a bell tone at the central office, and the operator would pick up the line, signaled by the bell tone, and the operator would say, number, please. And then you would say, I want, and usually you would give the central office that they want to connect to through a trunk, plus some extension. Murray Hill 78223. So Murray Hill was a place that had its own central office, and the operator had to set up a manual circuit-switched network connection. And so what the operator would do is the operator would, as part of the protocol, say, just a minute, and then take a patch cord, run you into the trunk that goes into the other central office, tell the other central office what the extension is so that that extension will start to ring, and then you would have your connection. That setup time could take a while. Fast operators did it in about 11 seconds. And then you had a guaranteed quality of service because you had a direct copper link between your carbon microphone and your receiver and the other party's carbon microphone and their receiver. So at some level, that was a circuit-switched connection with a real circuit that had to be physically switched by the operator. Right? That's a circuit-switch connection. Now, as it happens, when you start to think about passing a message from one person to another, right, that's not a circuit-switch connection. Right? If I send you a letter, that letter contains a message, it goes into a system, we'll call it the U.S. Postal System, and then eventually you'll get the letter. It's not a circuit-switched network, but it is communication. It is a communication network. So it's an unswitched network. Right? So then when we think about switched networks, in the case of, I'll call it the telephone, we have a circuit, and the operator uses a patch cord, and the patch cord gives us that circuit switching facility. And if you think about it, the operator was automated out of a job by something called a stepper relay, where the stepper relay gave you a series of different choices, and you could control how many steps the stepper relay had by using a dialer. The dialer would create a series of pulses, and every time you hit the dial and it went around to a different number, it would create that many pulses, and it would cause the stepper relay to increment. Then when you did it again, it went to the next stage of the next stepper relay. And you could have 7 stages for a 7-digit number, and then maybe another 3 stages. In other words, what happened was you became the operator, and you started to control the circuit switch network. But it was still a circuit switch network. and you still had a dedicated line. Later, what happened was people started to use digitization. And in digitization, we have two things that go on. Does anybody know what they are? How do you digitize a signal? What does that mean, digitize a signal? It's a common term. You've heard it before. You know what it means, especially if you've taken a course in signal processing. What does it mean to digitize a signal? There are two things that you do in order to take an analog signal and put it into a computer. The first thing you do is, and then yes, Rich.
Sample and quantize?
Yes. First you sample the signal by taking a section of time and defining what's called a sample rate. And you say, well, I'm going to sample the signal at 8,000 samples per second. Therefore, every 1/8,000th of a second, I'm going to grab some value. And then quantization, what does that mean? What does it mean to quantize a signal? Signals are varying continuously as voltages, right? They're like floating point numbers that vary continuously. How many numbers are there between 0 and 1? And the answer is an infinite number, right? Because real numbers can be represented in this way. But we don't have an infinite number of numbers in an A to D converter. We have a finite number of numbers. And therefore, we must quantize the voltage into specific levels. So if you said to me, I have an 8-bit A to D converter, then I have 2 to the 8 different possible quantization levels, which means I have only 256 different possible voltages. What does that mean to me, the programmer? It means I'm going to get an integer, a number, that is between 0 and 255. And that is how I quantize this voltage, which might range from 0 to 1. So in effect, it automatically builds in a signal-to-noise ratio equal to 1/255th of a volt. Right? That's your quantization noise. And your maximum signal will be 1 volt. So then, if you want a signal-to-noise ratio, it's 1 volt divided by 1/255th of a volt. And then you can take the log of that, and you get a signal-to-noise ratio in dB when you multiply by 10. And we'll discuss logs later. But that's a critical computation when you're dealing with communications. People are always talking about their signal-to-noise ratio. This is a measure of how much, I'll say, how many bits you actually have. Usually it's like 6 dB per bit is the rule of thumb. And we'll talk about that later. Here's a unswitched broadcast network, and I think it was one of the first ones mentioned. Radio broadcast, that's unswitched. Satellite, it's unswitched. Packet radio is an unswitched network. Packet radio is a store and forward network. And if you think about the letter that you send to a friend, it's a store and forward network as well. Because what you're doing is you're taking the letter and you put it in the mailbox. And what does it do? It sits there until the carrier picks it up. And then what does the carrier do? Brings it to some other mail facility where it sits until it gets sorted, and then somebody else picks it up and drops it off. So sending a letter, that's a store and forward network, also not a circuit switch network. What about this business about packet radio? Has anybody here ever done ham radio? No? This used to be a popular hobby. Does anybody have a ham radio license here? No? I'm the only one? I feel like such an ancient person. It turns out in the old days, when ham radio was popular, we had packet radio systems. In packet radio systems, and there are towers all over the place, you might not know about these things, you can essentially take your handheld transceiver and turn it into a data accessory for a computer. And you can transmit from one computer to another using a store and forward mechanism, not a circuit switch mechanism, in order to be able to get the packets from one place to another. Well, it turns out the old circuit switch networks that we were used to when an operator would pick up the phone and say, "What number, please?" are no longer in use. Instead, what we have are called virtual circuit switch networks. In virtual circuit switch networks, it feels like you have a direct connection to your other party. But in fact, you don't. You're sharing the media with so many other people. And the reason why it feels like you have a direct connection is that you have a guaranteed quality of service that guarantees latency and guarantees your signal-to-noise ratio and guarantees your bandwidth. And that guaranteed quality of service is not available to you in normal internet-based voice-over IP systems, which is why some of those sound like you have a lot of latency, a lot of delay when you go and start to talk to the other party. So I'll say this about that. Virtual circuit switch networks in a phone system that is run by a proper phone company are really different than the data packet switch networks that are being used for doing things like moving Skype phone calls from one place to another. But those data packet switch networks are getting very fast, and the bandwidth is getting very good, and the latency is getting very low. So Kyle and I can have a Skype phone call, and it sounds good. But there was still a little bit of delay, and there was always a pause after somebody was done before you started to talk. You were in Galway at the time. I don't know how far that is, but I'm thinking it's like 3,000 miles away or something or other. Far, right? Far. And I was talking with somebody in Saudi Arabia over the weekend, and I can tell you that when they turned on the video, it all broke up. They had to turn it off before we could have a proper conversation. There was no guarantee for quality of service there. But it was still a good phone call. It sounded fine. In a network, people like to talk about two kinds of networks. They talk about local area networks and wide area networks. A local area network is one where everybody kind of is able to see everybody else's data, and they have shared media. So when I transmit what I'll call multicast packets out of, let's say, one of these Dell computers, all the other Dell computers will see it. There's no network traffic isolation. But if you're in a wide area network, to go from the shared media that's local to all these computers out to, let's say, some other local area network, you need a bridge or a gateway. Some people will call it a router. And it will let you go from one local area network to another. And that's internetworking. So there's two kinds of internet, right? There's internet with the capital I. That's the one everybody uses, that everyone talks about. And then there's internetworking. That's when you take two local area networks and you bridge them together. And so you can have internetworking without being on the internet. So when we get together with our Arduinos and our little networking boards and we start to network with each other, they won't want us on the campus network. Right? We shouldn't be internetworking with them. We'll be on our own local area network. We'll have our own hub and we'll do our own thing. And that's fine, because then you can do whatever you want. And you can administer the network yourself and assign your own IP addresses and whatever you like. In networking, sometimes we think about layers. The layers of a network define the roles. The roles of the different abstraction layers are well defined in what's called an OSI model. And the OSI model classically consists of 7 layers. And it's a model that I like to use because I liken it to the different roles that you experience when you start to network computers together. And that first layer is a layer in which point-to-point communications can occur. And so when you see this picture here about the dish, there's no networking that involves I'll call it wide area network. Instead, there is a point-to-point protocol being used, where this dish on the left is talking to the other dish on the right. And the data could transmit in one direction or in both directions. And you can't tell by looking. Here's a local area network example that's quite common, known as the bus topology. In the bus topology, you have a media access control layer where all the different nodes can see each other's traffic. In that bus topology, if you're sharing the bandwidth with all the other nodes on this network, then what happens when you begin to get near 100% utilization is you get very poor quality of service. Think about the highway. Right? When is the highway really excellent to use? And the answer is when no one else is there. Right? When is the highway most efficient in terms of its throughput and getting people to flow? Well, the answer is when there's no traffic jams. Right? But if you go to 100% utilization in the highway, what happens? Traffic stops, right? You can't move. So 100% utilization on the highway is not desirable because they're sharing the media. And in a shared media system, like the highway with traffic, you have a problem, right? You have a media access control layer. In California, what do when the highway gets crowded? They put stoplights on the entrance ramps. And you can't get on that highway unless that stoplight turns green. So they try to control how much traffic goes into the highway. I used to live in California. You couldn't go from one place to another, no matter how close, in under 45 minutes because traffic was terrible all the time. Here's another, we'll call it topology. This is just the geometry of the network. It's called a ring topology. In the ring topology, all of the stations are able to communicate with each other, but not at the same time. Only one station gets to talk at one time. And so the question of who gets to use the network is decided by what's known as a token. And the token is held onto by a station until it's done, and then it releases the token for the next station to use the network. And this way you have a very controlled protocol for what's called sharing the media. It's almost like saying, I can use the highway and no one else can use it. So I got great access to the highway. And then when I'm done, you can use the highway. Well, that's very similar to the telephone, right? With the telephone, if somebody's on the phone, it's in use. You can't use it. That's a consumed resource. Same thing with a serial port on a computer. If you've got a program that's using the serial port, no other program should be able to write data or read data from that serial port because it's a consumed resource. So there's a couple of different models. I made allusion to the first model already called the OSI model. That's called the Open Software Interconnect model, and that has 7 layers. But there are other people who have a 3-layer model. And in the 3-layer model, they've got a network layer where the internetworking occurs, the transport layer where they have the role of flow control and error detection or correction, and then an application layer where some file transfer protocol program is running. And then there are a couple of things that happen in this course which kind of bother me a little bit, but there's not a whole lot I can do about it because it's the field, right? The field has a lot of nomenclature, a lot of jargon, and these terms of the field, which I use perhaps too casually, need to be defined carefully, and they have to be used consistently. And so one of the ways in which I do that is I introduce the new terms, hopefully gradually, but if I use a term and you don't know what it means or you forgot, just ask. And in this course, I'm real interested in just having you shout out with your questions. Don't have to stand on ceremony. Don't have to raise your hand. Just interrupt me. Don't hold your questions till the end of the lecture or till after the lecture because I don't want that. I would rather deal with your questions right away. So, ANSI, what's that stand for? ANSI. Yes, it's standard. It's American National Standards Institute. They have definition. Simplex communication means one direction only. Duplex means Two-way communication, most people don't say full duplex, but if they do say full duplex, it means two-way communication at the same time. And half duplex, that's two-way, but not at the same time. But if somebody says duplex, you assume that they can do two-way. But if you don't know if it's full or half duplex, you kind of have to ask, or just assume that it's full duplex. There's a French term for CCITT, and I can never remember it because I don't speak French. International Telegraphic and Telephone Consultative Committee, I guess. And they have their own sort of nomenclature, and it's unfortunate. They just say duplex means full duplex, simplex means half duplex, whereas ANSI says simplex means one direction only. So this is one of those things where the nomenclature in the field doesn't agree, and that's a pain. You know, if the two standards organizations can't agree on what the standard definition is, what hope do we, as mere computer network students, have to come across any kind of consistency? But you kind of have to be aware that even within the professionals in the field, there's no agreement. And that kind of stinks. And in fact, I believe that this is indicative of failing in the entire field. It evolved so quickly that the standards never really got properly standardized. And I'll give you a good example. For example, the serial port. Okay? Serial port sounds like it should be a relatively simple thing. You go onto a Windows computer, it's called the COM port. And it's a little D connect with perhaps 15 pins on it. Or is it 9 pins? I forget now. Maybe it's 9 pins. I have to look. Wait. Well, I'm looking at the COM port here, and it looks like 1, 2, 3, 4, 5, 6, 7, 8. Yeah, it's like 9 pins. So it's a 9-pin D connect on the back of the Dell computer, but it happens to be a male with a chassis mount. You go onto a Mac, there isn't one, or at least not anymore. But when there was, it was a circular 8-pin D connect. You go on a Roomba robot, it's a circular 8-pin D connect. You go onto any one of the robots that we have in our robotics lab, it's a 25-pin D connect. In other words, people use whatever they want. Right? It's a circus. There's no standards. And they've been doing this since the 60s, so there's a legacy involved in serial ports. And I say, what a shame. Isn't that terrible? Because no one can standardize on these things. Everybody's building cables to translate from one standard to another. Total unnecessary expense. Right? But there's no standard for it. I think Apple is guilty of doing a lot of interesting things with fancy connectors that are leading to terribly expensive cables. Right? They have these funky things that go into their iPads. They call them lightning connectors, and then at the other end it's a VGA connector, and then they have the temerity to charge you like $50 for the cable. That's so typical, right? And why are they doing this? And we see this all the time, and for no good reason I can see. So you want standards? This is one of those courses. We got standards. ISO is an international standards organization. ANSI is the American National Standards Institute. CCITT is that consultative telephone technology, whatever. I forgot already. And I just read it. And OSI, the Open Systems Interconnection model, is the 7-layer model used to describe networks. And that's the one that I'd like you guys to try and learn. So that's a standard. It's an international standard. It's not an American standard, but everybody seems to know it. And I'll just run through the layers for you real quick. There's a physical layer. That's the first layer. Then there's a data link layer. Then there's a network layer. Then there's a transport layer. Then there's a presentation layer, and then comes an application layer. And let's see if we can't go through these real quick by defining them and what their roles are. In the physical layer, what can you think of in terms of what might be a physical layer thing? What would be physical? Yeah, wire. Sure. How about if it's Wi-Fi? Is that physical layer? Yeah, because it's energy. Anything with energy going from one place to another. Who would be in charge of designing things that are in the physical layer? Who? Engineers. But what kind of engineers? Hardware, electrical engineers. Sure, not mechanical, right? And certainly not the software guys. It would have to be either the computer or the double E's. So if you're thinking in terms of creating a new network at the physical layer, if you want to work in the area of microwaves, that's probably an electrical engineer, right? Because electrical engineers are schooled in the area of antenna design. And computer engineers, well, if they're using antennas, it's because they're interesting in doing new things. I think we're doing... Does anybody have a fractal antenna on them? We don't bring that with us, do we? No. Well, we're working with a new antenna in the microwave realm, but I'll call that the physical layer. Right? That's physical layer. Right? If I told you, oh, here's a Bluetooth antenna, physical layer. Then comes the data link layer. This is where protocols happen that packets might be used, although in the world of OSI ISO, we call it DLPDU, or data link layer protocol data unit. Right? What would the data link layer protocol data unit be? It's a group of bits. And that group of bits in Ethernet might be called an Ethernet frame. In packet radio, it might be called a packet. In some other transmission system, let's say in a modem going from one end of the phone line to the other, you know, that's a modulation scheme that uses a link access protocol, and that's point-to-point protocol. That's a data link layer. So anything that's point-to-point protocol is data link layer. And what it's trying to do is manage the transmission of data from one place to another. In data link layer protocol, you might be able to say something like this. My packets are getting a lot of errors and I have to retransmit them a lot. Let's make the packets smaller so you can negotiate the size of your packets with your transmitter and say, I'm getting too many errors. I'm asking for too many retransmissions. Back off a little bit. Slow down the data rate. And this enables you to transmit more reliably. And transmitting more reliably may actually mean that you have to transmit slower. But overall, on average, that might mean that you can move the data faster. Oddly enough, slowing down and being more reliable can make data transmission happen faster. Because if you go really fast and make a lot of mistakes and you have to do it over, that's not going to help your overall throughput. Sometimes this happens, like if you have a typing exam and you have to type and they're grading you on your typing errors. If you make a lot of errors, it counts heavily against you in terms of words per minute because you have to go back and correct those errors. So being correct in your transmission is sort of important. Data link layers can be responsible for doing things like error correction and error detection. And those two things are different and also very important. Data link layer, that's the first stop that happens after the physical layer. It's so important that you have reliable transmission. Then comes routing. And routing, that's what gets you from the local area network to the wide area network. That's what enables internetworking. And so you can sort of see that's a very different function, totally different role. And what does routing really do? What it says is, well, here's a packet with an address. Oh, it doesn't belong on any computer on this network. Let's give it to the router. And the router says, oh, that belongs to this other router. And it's basically playing the role of the operator, saying, what central office does this belong to? And it opens up a trunk so that the packet gets to the right place eventually. Then comes this transport layer. And transport layer You've heard of this before, but you didn't know you were in the transport layer. If you were in the Internet protocol layer where routing happens, you'd call it IP. But if you're in the transport layer, then you're in TCP. Isn't that interesting? So TCP on IP is what we now call TCP/IP. Well, it turns out with transmission control protocol, you can go back to the transmitter and say, stop sending data so fast. You can control the flow. So what that means to me, the receiver is, if I'm getting swamped by data and I can't handle it, I can turn the transmitter off for a while until I catch up. That's so important because maybe I've got to do something in order to be able to take those packets you're sending me and reorder them and reassemble them into something coherent. Because a stream of data is really nothing more than an unformatted sequence of bytes. You're up to like chapter 15 in the book now, right? So that's what you got to, right? You got into the streams. And so a stream of data is giving you a pipe. And that pipe is really nothing more than bits that come out from one end and then come into another end. And what you're doing with TCP/IP is you're delegating that pipe, which we call in programming parlance a socket. You're delegating that to the lower layers of the network. You, as a network programmer, normally don't get involved with routing. You, as a network programmer, don't normally get involved with flow control. You, as a network programmer, normally expect that the data you push in one end is going to come out the other end. And you can take all of those network services for granted. And isn't that fantastic? That means that you can transmit a file from one place to another, and that place that you're transmitting to could be anywhere on the planet. And presumably, it'll get there. Because all of the flow control and all of the error handling is handled for you by the network services. Right? So that means what? I can write a program that transmits a file to Japan. And I don't even have to care that it's in Japan, because the network layers are reliable. And they will get the packets to route to the destination somehow, and I don't have to care how it goes. And eventually it'll get there and get reassembled in the right order and be corrected for error, and I'll have the file at the destination. That's the transport layer. The session layer, that's where you're doing your login. That's where you're going to go through the security protocol that allows you to be able to gain access to file data. This is so important because if you have a socket and you've opened up this connection, it's very much like picking up the telephone and starting to dial. The establishment of that connection is a lot of service. That's the service the operator used to supply. But now you've got to be able to do that in a layer that has that role. And so the session layer is really the operator that essentially lets you pick up the phone and establish that connection across the transport. Presentation layer has to do with translating the data from one format to another. So if you told me, well, gee, I'm using bits where the least I'm using bytes where the least significant bit is on the left, and someone else is using bytes where the least significant bit is on the right, it's in the presentation layer where they get flipped. That's key. So there are other things that go on where people are using interesting character sets. There's a relatively new character set called Unicode, which we use in Java, and that is a 16-bit character set. And that gives us 65,536 different characters. Well, in certain languages like katakana, that's not enough. Ideographic languages have different ideographs for every word. And so what that means to me is that I can probably use the 65,536 most common ideographs in katakana, but not necessarily find all of them. And there are some ancient ones which have gone into disuse. So modern katakana could be working okay. So that presentation layer and character code conversion can take on a wide variety of different characters. And then on top of that comes the application layer. And if you're thinking in terms of applications, you might say, well, geez, I've got this protocol that is used within, let's say, Internet Explorer or Chrome. And that protocol is HTTP, right? Hypertext Transfer Protocol. Well, if you're using HTTP protocol, you're in the presentation layer. And if you are running an application on top of it, like a browser, well, that's the application layer. So presentation layer protocols often involve special formats. For example, in the presentation layer, maybe there's a language that you use called HTML. And in HTML, that markup language, you have HTTP, which uses a protocol that says get and then puts in a file name like index.html, and then the HTML comes down, and then in the I'll say application layer, the browser renders the HTML onto the screen. So that's kind of an important layer. We're often, as programmers, working to generate dynamic HTML so that we can have a web page that represents the current state of some data structure, like the temperature at the present time, or maybe even allow us to input data, like move the servo to a certain place, or here's my username and credit card number and charge me a bunch of money so I can have my goodies, things like that. So here are all the protocols all at once. When you're thinking in terms of where you are in the book, there's a separate chapter on networking. And I talk about this very diagram, and you can see the 7 protocols. Nobody says data link protocol units. Often I hear the term frame bandied about. Nobody says transport protocol data unit. I hear TCP, right? That's what I hear. So while OSI has settled on specific name session protocol data unit, nobody says that. Not in any real network I know of. So when you get into the real networks that you encounter, you'll hear TCP/IP. Sometimes you'll hear TCP/UDP for user datagram protocol, which is a little bit different than TCP/IP. So, you will see that there are different protocols out there. And not everything is Ethernet. There's ChaosNet, there's other kinds of nets, and not everything is using these bus topology networks. For example, the IBM cell processor uses a token ring network with perhaps 8 cores. And I think they put that in the PlayStation now, although I'm not sure if it's still there. Maybe they used to. It was considered a high-performance supercomputer at the time, but it was very important that you knew how to program it. And they changed it. What are they using now? They're using Intel inside. Oh, okay.
They changed it to pretty standard.
Oh, so they're using an 8-core, and they've gone to the Intel inside, x86 architecture. Yeah. AMD, as far as I know, only uses x86 architecture, or maybe what you call x64, or whatever they're calling their. x86-64. Yeah, -64. Yeah. Turns out there are compelling arguments for going with standards, particularly if everyone has got the tools for compiling to them. So that's my little intro to networking, such as it is. What I also wanted to do was I wanted to kind of get back to the reading. And in the reading, I think we got through an introduction to Java, and I talked a little bit about well, I wonder if you've gotten to talk about why people like Java. What's so good about Java? Portable, right? Transferable, portable. one of the things about Java is if you run an applet, right, you can run it just by visiting a web page, and the applet runs, right? But then the question became, if you could run a program on demand just by visiting a web page, would you? Right? And the answer is no, because it doesn't feel like it would be safe. So where does Java get its safety? Why should Java be safe? And some people would say it's not safe, therefore disable it. I think the Department of Defense said that or something or other. Where does Java get its security? Yes, sir. Oh, users give permission. But what if a user doesn't give permission? Does that mean you can't run Java? Yeah, you're operating with an instance of the security manager, which is immutable. You can't change it, and it gives you security through restrictions. You can't open up a file system object. You can't go in open up a connection other than a connection to the server. You can't send an email other than an email through the server. Certain restrictions exist when you're running inside of this default sandbox. Then when you try to run something outside the sandbox, usually you have to put a certificate in place and do what's called signing of the jar file. And then when the jar file is signed with a certificate, before it's run, the browser or whatever it is you're using to run the jar file asks you if you trust the author. Right? So if the author is Doug Lyon, it might say something like, do you trust Doug Lyon? And if the answer is no, then do not run his program. Right? But of course, what's happened now is I've increased the amount of liability that I am going to experience, because if I sign something and it does something bad to your machine, then you're going to be mad at me. And now I have, if my program goes in and does some viral thing and deletes your files or steals your identity or whatever, and you have to go through the rest of your life and you don't know who you are because I stole your identity, then what do? You end up suing me. So I have incurred liability by signing these jar files. So I have to be careful about which jar files I sign. Let's see now. We talked about nested classes last time. Did we talk about multi-threading, multitasking? Yeah, a little bit. Okay. And files, I think have we used files at all in this class? No? Shall we do a file review? Let's do that. Let's talk a little bit about files. Files are a repository for data. I like to say it's a place for my bits, and I take the bits and I open up the file and I can stick the bits in there. And then when I'm done, I close the file, and when I want the bits back, I open up the file and I grab the bits out. Bits go in, bits come out. So what's the big deal? I store the files in a semi-permanent place so that they are retained. I like to think that they are on the hard disk and not the RAM. And I also like to think that RAM and hard disk drives are about 1 million times different in terms of their speed, right? Where do you get that? Well, if RAM access time is in nanoseconds, that's 1 times 10 to the minus 9. If disk access time is in milliseconds, that's 1 times 10 to the minus 3. And the difference between 9 and 3 is like 6. So the speed of RAM is, generally speaking, not in the same zip code as the speed of the disk drive. It's so slow. On the other hand, disk drives are huge. I go to Walmart, I plunk down $60, and I get a 2 terabyte external hard drive. Getting a 2 terabyte solid state drive would probably require me to mortgage the house. Right? It's one of those things where I'd love to have it, but I can't afford it. So, I mean, if I go and buy a solid state drive, maybe I could afford, 128 gigs or something, or 250 gigs. And usually it's like $1 a gig when you get into the solid state drives. And even though they're solid-state drives, they're almost never as fast as real computer RAM because they're going through some sort of hard drive interface, and that bottlenecks your ability to have access to these things. And even worse, they have limited life. So after 100,000 reads and writes to the same place, they're dead. And from my point of view, if you take a USB drive and plug it in as your main hard disk, or if you've got a Raspberry Pi and you have a compact flash drive and you're trying to do virtual memory out to this thing without evenly distributing your file system reads and writes, that compact flash drive is going to have very limited life. 6 months later, bam, it's gone. And once it's worn out, well, that's it. It's dead. Just swap it out. Get a new one. So this is one of those things where there's a clear cost-performance trade-off. It's speed versus size. That is such a consistent trade-off in computer science. Speed versus time. You're always trading off speed and time. It reminds me of a song. It's about encryption. Super polylogarithmic sub-exponential functions. Faster than a polyglot, slower than exponential. Even though they're hard to say, they're really quintessential. Super polylogarithmic sub-exponential functions. Um-diddle-diddle, um-diddle-I, um-diddle-diddle, um-diddle-I. Oh, makes the phone ring. A coincidence? I think not. Ignore. Here, let me fix that. So the bottom line is most computations can dissipate a lot of energy. We can trade the heat with water, but there's a better strategy. The laws of thermodynamics do not apply when physics is not tuned. So physics does not require that power be consumed. Super polylogarithmic sub-exponential function. And then what they say is you can trade space for time. And I can't hardly remember this section, but it says the space will grow according to the exponential. So trade off time to save on space. This really is essential.
You have that on your
No, I don't. So it's one of those things. Space and time is such a common theme in computer science. I kind of got thrown for a loop because somebody was ringing the cell phone and it sort of screwed me up. But it's one of those things where space and time is such a common trade-off in computer science that you see it all the time in algorithms. That's cell phones. You must control your cell phone or your cell phone will control you. So when I think about file systems, I think about little toolkits that I have available to me for doing basic stuff. Here's a program which I was trying to demo the other day. Let's see if I can get to some of these other screens. Here's a screen that comes off of it. And if I go into the Edit menu, Preferences, Serial Port Setup, yep, there it is. This serial port, it says, oops, try it again. Serial port setup. This serial port is called a COM port under Windows, and you get to set the data rate for the COM port. You get to set the number of data bits that you use in a word, the number of parity bits, that's a kind of error detection or error control, the number of stop bits, that's what's called a framing bit, which tells you when the data bits for a word start or stop, and then the kind of flow control you can get. This is point-to-point protocol called data link layer. Well, guess what? When you open up a COM port, it's really a file. If you're on a Mac and you go to /dev and then you type in ls, you'll find all the USB dongles that you have plugged in, which have been turned into COM ports. You'll find the Arduino is in there. It's all part of your file system. That's how Unix does it. Windows is somewhat different. Windows, you can't find the COM ports in the file system. But when you do file I/O to the COM port on the Mac, you're really communicating to a serial port. It's not going to the disk, but it feels like a file, and it has a file descriptor. So that's an interesting point. And I don't know if you noticed, but last time when I did this, it didn't work properly because I was using pure Java instead of Java native interfaces, and I hadn't finished the migration. So now I can go to the serial port and it opens up properly. It's a small bug in my program. I hadn't debugged it properly for Windows. I had debugged it on the Mac. But it's a little address book program. No, they discontinued the API service. Yeah, they will no longer allow people to do data mining with Yahoo and points of interest. What a pain, right? I can't do it. Yeah, they stopped it. I don't know of any alternative API for doing that. I mean, it'd be cool if they could bring it back, but I don't think they will. If you read the book on files, my book, you'll find there's a separate package called Feudals. I think it says something like resistance is feudal. Feudal is file utilities, and this is where I keep all of my tools for doing file I/O. And within Feudals, I have a toolkit called Feudals. So it's feudals.feudal. And if you want to, you can find some nice examples. In the book, I think I put in some file examples in here, Chapter 14. So let's see now. Here's a file example. And this says get dir example. Let's see if this works. Run. And welcome to my file examples. Oh, how cool. There. How's that for a directory tree structure? That's fancy, huh? Isn't that fancy? If I click OK, what does that do for me? It tells me what I selected. So what I've done is I've given you a really fancy file tree, and you can navigate through the directory structure and select directories. But for most applications, you won't want anything so fancy, I think. Disconnect. Yes, please. Let's try a simple file example. I will start something new just so you can see it from scratch. Let's see, Java class. Let's give this read file example. So let's see what we can do to get a file which we can use for read. And I'll make up a main method, PSVM, Control J main. And then we'll get something of file type, file F, equals Alt-Enter to import file I/O. So this is part of what I'll call the file I/O package. And let's see now. Java I/O, the Java I/O package. And we'll say file F equals feudal dot get read file, and we'll prompt the user to select a GIF image. Select a GIF image. How's that? Alt-Enter. And then what we'll do is we'll print it out, SOUT, Control-J, Enter, and we'll print out the file, and we'll say f.get absolute path. See what that prints. So Feudal is a GUI agnostic mechanism for creating a standard file open dialog box. If you want to, you can set Feudal to use Swing, or you can set it to use AWT. And I think if there was some other toolkit like SWT for Eclipse, I would use that too. So here's my little file. We'll open. and it gives me a fully qualified path name. How's that for file I/O? So now I've got input. Right? So now the question is, how would I take this file and list it to the console? Suppose it's a text file and I want to read it. That is to say, I would like to have a way to get the whole file all at once. Well, in Feudal, I can get read. Oh, I know how to do this. Let's see. I think I know how to do this. Reader util dot get file as one big string. Ah, that's a good one. Get file as one big string. F. Put that in. Semicolon. Pretty cool. So now I can put in a string. S equals get file as one big string. And then SOUT, Control J, Enter, print the string. Well, we'll have to expand on those tools so that you can see the details on how they've been implemented. But before I do that, I thought it would be fun to do the demo. So let's just run it and see how it works. Because it'd be really bad if I showed you how it all worked without actually showing that it does work, and then found out it didn't work. That would suck. So let's find out if it works first, and then we'll do a little analysis. So what can I read here? I can't read exe files. I need like real data. Do I have like real data here? J for P? There should be like some real data somewhere. Oh, I know. Let's have it print out itself. Oh, that's a good idea. Very recursive. So we'll go into the files. What's the name of this thing now? Read file example. So the read file example will print out itself. That sounds like something. And there it is. So the read file example was able to read itself and then print itself out. Good, right? Isn't that fun? A file that reads itself and then prints itself out. How about if we look at how some of this stuff is implemented? Should we do that? It's an analysis. Right? There are a couple of ways I can do it. If I type on click get read file and then do Control B, we can see what I mean when I say this is GUI agnostic. I first check to see if we're in swing or not. If we're in swing, it'll do the get read swing file thing. And if we're not, it'll do the get read AWT file thing. Not only that, but it stores the last place it's been. That way you don't have to start at the root of the file system. In other words, this is not your father's Oldsmobile. This is going to essentially remember where it's been. And that's kind of important, because if you've been in a specific directory when you last opened a file, then when you go to open the file next, it's very common for you to be in a very similar place. So if you put your data in, I don't know, C:\lion \J for P \data, like I do, next time you open a file, you'll be there in the data directory looking for data to get, rather than starting from the root, which is what happens by default. So not being able to remember the last place you were last time you opened a file is classic forgetfulness that you get for people who are suffering from what's known as Kirchhoff's psychosis, which is what you get when you're an alcoholic. You can't remember something from like yesterday. So I think what happens with GUIs is they typically suffer from Kirchhoff's psychosis. And this is my way of fighting that. So what I do, and this is kind of fancy, really. This is much fancier than your average file open dialog box. I not only dispatch on whether or not you're in swing, but I have a thing called the file bean. and the file bean stores in your preferences the last place you were, both for reading files and another place for writing files. And in this way, reading and writing files are retained from one run to the other, even if you reboot the computer, because it's stored in your preferences. And those preferences are your user preferences, and those user preferences are as secure as the login to your domain. So that means you can change computers, and your preferences will still be retained. It'll still remember the last place you were. So that's kind of cool, as long as the computers are sharing domains, domain controllers. Kind of fancy. So let's see how we can get a swing read file. Given the last input directory from the file bean, FB, we'll get a directory, and we'll use that directory to create a JFile chooser. So that directory was retained from the file bean. That's kind of cool. Let's see what happens if we run this program again. And look at that. It started from chapter 14, files. That's the last place we were. So it retained the location. Let's see if we can do the copy directory. That's pretty cool. Now let's do this again, only this time with a difference. This time we'll change the look and feel of the file open facility by going to feudal and say set feudal dot. Oh, I know how to do this. Sorry, I forgot my own code. I think it's a global. Find is swing. FB is swing. File bean. I think I have to restore the file bean and set swing to be false. Let's see if I can do that. Just for fun. File bean FB equals file bean dot restore. File preferences bean restore. So this should be a file bean, file preferences bean, paste. Here's restore. And what does he want? Serializable. I got to pass in a class. And this class is not serializable. I better not use it. It's going to get too complicated. I just realized. Can't do that here. Let's see if I can do it here. File feudal dot get file bean. Nope, he won't let me do it. Darn it. Oh, he did do a restore. It's feudal bean. I thought it was file bean, but it's really feudal bean. Well, if I said something like this, FB dot set swing to false, that would set it to false, and then you would be able to save it and proceed to use it as an AWT graphic user interface. It's funny that I totally forgot about that. So I thought it was called file bean, but it's really called feudal bean. Not a good example. Sorry about that. Sorry for my blemishes. Paste. Okay. FB dot set swing to false. And now when we get a read file, it should work. In theory, And now it's using a different user interface. In this case, it's using the standard file dialog box for Windows. The standard file dialog box for Windows looks remarkably different than the one for Swing. And if you were on a Mac, it would look like the standard file dialog for Mac. And if you were under X, it would look like the standard file dialog for X11. So now what you have is the ability to go into the heavyweight graphic user interface supplied by the operating system. I just canceled instead of selecting a dialog. Let's make that true. Try it again. And yeah, it doesn't quite look right. Open. Close. Run it once more. Now he's doing everything with AWT, and he's not changing it. I think I forgot to do a save. fb.save. There, now it works. And he forgot where he was. So I've got to set the location, and then he should retain it. I want J for P. You should be in here somewhere. I think you must be on the C drive. Just a minute. Bear with me a moment. J for P. SRC. And we were in Book Examples, Chapter 14. And Read File Example. And we're there. Next time I run it, it remembers, which is just what you want. And you can see why it's such a pain when it doesn't remember. So what about this get file is one big string? What this is doing is it's populating a string buffer. And my reader is a buffered reader. When you go and open up a file, you can either open it up as an unformatted sequence of bytes, or you can open it up as a sequence of Unicode characters. If you open it up as Unicode characters, you're using a reader. And what that does is it interprets the bytes that come in as Unicode, which means you can get a string directly from it. So then when you go and you get a buffered reader, what that's doing is it's reading in a sequence of characters, and then when you do get reader as string array, is it does what I would call an idiom. Yeah. The idiom in this language is to put in a while loop in there and keep doing a br.readline, a buffered reader.readline, until you get null. Once you get null, that means you're at the end of the file. You see these kinds of idioms in C, in C++, and C#. This is just a classic sort of thing. And vector add element is being used because we just don't know how many times we're going to end up reading the file. We don't allocate space in advance because the file could be of unlimited length. What's the drawback of doing this read all at once operation? What could go wrong? What could possibly go wrong? You could run out of memory, right? If it's reading it in all at once, it should be efficient if you have enough memory. But if you have big files, then this is not the way to go. So if you're trying to process stuff all at once, this is a reasonable thing. Now what I did was I set up a little a Blackboard homework for next week. Was it for next week, or maybe it's for 2 weeks? 2 weeks. It's probably for 2 weeks. Next week? It's next week?
Yeah, if you want to make it 2 weeks.
I can make it 2 weeks? Is it 2 weeks or next week? I forget now. Let's see now. See if we can get this homework in here. It's under course content, and it's called, oddly enough, Homework 2. Data mining. You're given a URL. What does this thing do?
URL doesn't work, by the way.
The URL doesn't work, and does it say when it's due?
Yes.
Where does it say?
Click it.
Oh, you have to click it? Wednesday, February 5th. Is that next week?
Yeah.
That's Wednesday of next week. So that is next week. And the URL doesn't work. Really?
Yeah.
It used to work. Oh, you know why? It looks like it put a backslash in here. What else did it do wrong? Enter. Oh, maybe it still doesn't work. Oh, that's terrible. I gave you a URL that doesn't work. Oh, this is terrible. Isn't that awful? We'll have to fix that. So the goal is to use a URL for input and then write a program that will get the string associated with that URL and do a little data processing. But unfortunately, the URL is bad for whatever reason. Used to be good. And your goal is to take the HTML associated with that URL and convert it into a data structure, which is a text file consisting of comma-separated values. That was the goal. But since things aren't working, I think maybe we should take this homework 2 off the table, because things are... Why should the URL be bad? Do people know what the SEC is? Yes, that's true. And do people know what EGAR is? Electronic Data Gathering Archive. So the Security Exchange Commission, since 1996, has required that all publicly traded companies, except in exigent circumstances, file all of their financial records electronically with the Security Exchange Commission using their EGAR system. It's a government thing. It's your government at work, government hard at work. So what happens is they accumulate a lot of documents. I'll call it free-form financial narrative, as well as some very structured narrative in a wide variety of different markup languages, mostly called BRL for XML for business language, and also FIX for financial interchange for XML, or another form of XML language. But a lot of times what happens is you get free-form financial narrative with the formatting of HTML. And those HTML documents are documents which you can parse and read and use for your data mining. And so I had an interesting little financial data mining project for you. But I think maybe we'll put that on hold for now, since it seems to have a bug in it. My project has a bug. Not sure why. So when you get a file instance off of the file system, the file instance can be an instance of a file, or it can represent a directory, which can be a list of files. And in fact, a directory not only can contain files, it can contain other directories. So what you can do with the directory system is you can recursively traverse your file system. And a file system has a representation which is very similar to that of a tree, where the tree is a series of directed acyclic graph, which means that the The containers of the individual files don't cross over with one another, except perhaps if there's a shortcut, what they call an alias. And then there may be ways in which you can break the cycles, but that's an exigent circumstance. There are these things that you come across that I think really speak to the lack of standardization in the industry. And one of those things that you find is how you separate one directory from another. If you're on a Mac, people use a / to separate one directory from another. If you're in Windows, people use a / to separate one directory from another. Gee, can't we all just get along? Turns out that the industries have always fought with one another about how to standardize these things, and therefore there's no standard. The other aspect, sometimes I've seen on a Mac, the colon is used to separate one directory from another. What a mess. What a mess. And so if you think about it, the colon has very special meaning in DOS, because C colon, right? That's a big deal. You don't want to reuse the colon improperly. So how do you write, portable programs if your program doesn't know what operating system it's in? And the answer is the system class will allow you to get the path separator. So if you call system.getPathSeparator, it'll return the / or the \. It really is quite a mess. So in system.getProperty, quote, file separator, you'll be able to go and get the file separator that's used for your file system. It's really, unfortunate that people can't just get along on that stuff. Path separators. That, for a Windows system, is a semicolon. So when you go to edit your path in the System Administrator dialog box, you're using semicolons. And you've seen me do that before, I think. Right? You don't need to see that now, do you? No? It's one of those basic things. You've probably done this before. Go into the command prompt, type path, and what you see with fully qualified path names is semicolons here and backslashes for the directories. Well, it looks really different if you're on a Mac. If you're on a Mac and you've got the terminal prompt, which is in the utils folder, type in echo $path. On Windows, it just says path, but on a Mac, it'll expand the variable path with the $sign into its standard value. In Windows, if you just type set and hit enter, you can see all of the global variables and how they've been set. I don't know if you've ever tried this before, but there it is. Let's see if we can get back to the PowerPoint. So I've got my own way of getting path separators. I like to make my own toolkits for these things because I often forget stuff like what the string is that should be contained in the quotes when I want to go get the path separator. So by making a toolkit, it reminds me, kind of documents it. System utils, for me, does that. System utils is like the feudals, only for things like getting things like the path separator. Let's see now, what else do we need here? This is too much detail. But we've already seen getting read directories, getting write directories. What else do we want to see here? Interfaces. Okay. There's a thing called a file name filter. When you go to list all of the files in a directory, you can use the file name filter to determine whether or not the file is acceptable or not. So if the file ends with Java, you could say that's acceptable and we'll accept it. Then all you have to do is define the accept method, where the accept method takes a file name, a file instance, or maybe a name that you're looking for, and then creates some implementation that returns true or false. And then you can use that to explore your file system. And you could say, well, I think I want to delete all the class files, right? Because sometimes in Eclipse, they geographically co-locate the bytecodes or class files with the source code files. So to recursively delete all of these files in Windows, you could write a program that says if the file ends with .class, then you delete it. So deleting all the .class files requires recursively traversing the directory structure and then using some sort of a test to see whether or not that's a file you want to delete. Let's see now. That's an example of polymorphism. So everybody knows what polymorphism is? No? Polymorphism means many shapes, and it refers to multiple implementations that can be derived from a single interface. So if you have one interface, like the file name filter, all of the tools can make use of the file name filter in a consistent manner, like a plug-in component, but its implementation can be as complex as you like. And so what that means is you can create a framework that makes use of these interfaces, and the framework can be very complicated, but then the implementation of the interfaces is completely separate. I'll give you an example. Suppose you had a simple image processor interface. The input is an image and the output's an image. The operators could be very complicated. You could do all kinds of image processing. But then the framework for running those operators could just involve defining a region of interest for an image, or define a mechanism for opening images and saving images, and then you can plug in as many operators as you like. So by having completely separate plugins, if you decide to change the framework from, let's say, Swing to something that works on HTML or inside of a phone browser, you don't have to actually care how the operators are implemented because you've separated out the concerns. So in a sense, you have arrived at a mechanism for code reuse by using polymorphism. So here's an example where we list the files in a directory, and here's one that uses a file name filter. We don't know how the file name filter is implemented, but one thing we do know is it has an accept method, so that when the file comes in, it'll determine whether or not it should be listed. So the file name filter is using polymorphism because we have no idea what the shape is of the interface's implementation. You've probably seen dir in DOS. Gesundheit. ls is the way you would do that in Unix. So I created my own ls class, which is just like dir in DOS, and that lists all the files in a directory, and you can use a file name filter and choose how the directory files are listed. If you want to grab all the files in a subdirectory recursively, you can do things that are very dangerous, like delete them all. It's very easy to write a program that does serious damage to your file system. So this is your warning. It's a very powerful gun, and if you shoot yourself in the foot with it, don't come crying to me. It's especially onerous if you want to do damage. If you want to print all the files in a directory, that's okay. You want to list all the files, compile all the files, fine. You're going to delete all the files? You're on your own, buddy. But you can do it. You're a Java programmer, you can do it. Just call f.delete, where f is an instance of a file, and it's gone. And it's not going to ask you if you're sure. Okay? It just does it. Which is good and bad, depending upon how you look at it. So here's my get subdirectory example. It's asking for a prefix, a suffix, and a midfix, which says here's the wildcard I want to match in the beginning, the middle, and the end. So it could be something like F star ava dot CLA star, or something like this, whatever you like. And once I have that, I make what's called the wild filter. The wild filter implements the accept class. It has to start with the prefix. It has to end with the suffix. It has to contain the midfix. And that'll be the string representation of the file name. And then I pass the file name filter off to dirlist, which recursively gets all the files in the directory that unify with the wild filter. Once I get all those files, I can proceed to do something to them. Write a for loop, delete them all, whatever, copy them all. So the wild filter should be somewhere in futils, and we should be able to find it. Here's futils. Here's a bunch of filters. Here's one that says, is it a file? So if it's a file, with isFile, it returns true. Here's a date filter. If the file was created on a certain date, then it will be accepted. So you can see how complicated that can get. You can check for suffixes. You can check how you want to set the flags, whether or not it was created on a certain date or after a certain date. Date filters are kind of important if you want files that have been created recently or older files. Here's a dir list, and I'm going to see if I can just run the dir lister, and then we'll take a break. Select root directory, open, and there it is. Let's try a higher level root directory. Run. And you can see it remembers where it was, chapter 14. Let's go up a little bit. We'll go into the book examples. Let's list the book examples. And here's all the book examples. So that's handy, right? For data processing applications, being able to go through the whole directory structure, that's convenient. If you wanted to, you could delete all the files that end with .class, especially if they're geographically co-located with the .java files, like they sometimes do in Eclipse. That's why I don't use Eclipse. I've never been able to figure out how to keep all of the byte codes going to where I want them. I can't figure out how to keep them away from my source files. So I've got a couple of interesting things, detecting duplicate files, that sort of thing. I think that's all I've got for the file examples. Let's take a little break.